It's a pleasure to have Nitsan Ba from Weizmann talking about if it actually exists, a supernova bound on axion. Please.
Yeah, roughly speaking. So first, I want to thank the organizers for pulling this off. For me, it was it seemed like a long shot to have a conference. So thank you, and thank you especially to Filippo, also for inviting me to speak. So I'm going to talk about the supernova bound and whether there is such a bound. So it's not a new work, more than 2 years now. But I think the picture has remained kind of the same, more or less. This works. Oh, crap. The other one? Oh. Not yet. Maybe it's okay. Yeah. Okay, I'll forget about this. So I guess it's a complicated subject, so I don't want to get into too many technicalities, and I thought I'll give up some of the drama by going directly to the bottom line, which is the following. So some 34 years ago, we saw an explosion just outside our galaxy, as Jorge said, and helped me set up the stage, which was the first multi-messenger event where we measured both neutrinos and photons in many bands. And then the observations, mainly the neutrino signal, can be modeled in at least two ways, which are very distinct theoretically, but are comparable from a statistical point of view. Conventionally, what is assumed is that a significant part of the neutrino signal that is in duration was basically a cooling neutron star. And when you take this hypothesis as written in stone and you add on top of it some models of new physics, then you find that the joint hypothesis does not work, and you have to exclude some of these new models. So that's the usual approach. However, there is, in principle, an alternative possibility, which is that some of the neutrino signal came from accretion. And the accretions, namely the infall of matter, and losing, emitting the gravitational energy in the process, is a natural source of neutrino luminosity. And it's also, interestingly, insensitive to emission of new particles, for a reason that I'll show you in the later part of the talk. So I would say in our work, the main novelty is just to say that accretion is a process which, at least in the context of supernova, which is much less sensitive to the emission of new particles. Beyond that, what we did in the paper and what I'll do now is to tell you about kind of about the literature and the state of the art of the literature. But it's nothing that if you had really gone through the literature, you wouldn't find yourself. So that's the plan, to go through this in more detail. Okay. So I thought it's useful to start with first look at the data to put this into perspective. Folks. So there were basically 3 neutrino observatories that measured about 25 neutrinos over a duration of 12 seconds. And in such a picture that I'm showing you, there are things that enter like in inferring from this, you have to take into account thresholds and that time and efficiencies, etc. But this is just to give you a first look at the sparsity of the data and the main features. So it could be put in more data-driven way by looking for the, well, under general assumptions about the neutrino emission, you can derive an estimate for the neutrino luminosity, at least the anti-electron luminosity. So here you see such an estimate from Bloom and Kushner 2016, although I think earlier analysis would have agreed with this. So what can you learn from just staring at this? The zeroth order thing is the energy scale, which is about 10 to the 53 erg. And if you ask what is the energy that you need to expand to go from a Chandrasekhar level mass to a nuclear density, you find that this is roughly the energy scale. So it's strongly suggesting a core collapse origin for this signal. The next thing, sort of a first order, is that you see a decrease over a 10-second period. It's also Jorge mentioned, which perhaps suggests to you something like a cooling neutron star. Then you go to perhaps the second order, and you can see a dip at about 2 seconds, which could be a statistical fluke, but it could be telling us also something about how the star exploded. So I'll get to how people have interpreted this dip in a more interesting way in a bit. So the next thing I want to do is to go to the explosion models of supernova and talk a little about them. So the conventional model, the so-called neutrino-driven explosion. One second. I'm going to paint like a pictorial way, which doesn't do justice to the amount of sophistication that enters these calculations. And I might have even stolen these pictures in the past from Raffelt. I'm not quite sure. I'm sorry. So basically reiterating what Jorge has mentioned. So you have an iron core which starts to collapse, and in the process it gets very dense, very hot, emitting neutrinos among other things. The next thing is that it hardens at nuclear densities, still having accretion, having neutrinos. But when it hardens, it sends out a shock, bounce shock it's called, which doesn't go on for long. This is not the shock that explodes the star, because accretion and nuclear dissociation stops it. But then you still need an explosion. So if you look at the literature of the people simulating such models, they're telling you need two things. One is instabilities around the core of the star, and the second is you need some of the neutrinos that are emitted from the core to be reabsorbed in the just outside it. So you need roughly between 1% to 10%, depending who you ask, of the neutrinos to be reabsorbed. So that's already a tough problem, you see. But if it does work and you can make an explosion, so it should happen fairly quick, after a fraction of a second. So the way it looks, if you look again at the neutrino events, to put this into perspective, time-wise, is that the first fraction of a second, you have quite a few events there. So there you assume that the neutrinos that you saw came from accretion luminosity plus some neutron star cooling, proto-neutron star cooling. And then the model tells you you have an explosion, so afterwards, what is typically assumed in analysis of 87A is that the explosion takes place in a spherically symmetric way, and all you have left is a neutron star in the middle, which then cools off and gives you the observed signal. So I told you before that there is a dip. So for example, here, because it's a smooth neutron star cooling, it cannot explain this dip. But okay, it could be a statistical fluke. So how does the axion cooling enter this game here? So it's very simple. Because you only assume basically that you have a neutron star, then you ask how much more new physics can I push there? Like how high can I have the couplings such that it doesn't terminate the neutrino signal too fast? So here is a calculation from 89. I think largely the calculation remains similar in the sense of not having a full simulation that explodes. Like Jorge said, for example, nowadays they to do these new physics bounds, they push one-dimensional simulations to explode artificially. Here, I think it's only a neutron star on its own, assumed to be there. So you see, as you decrease the FA, the decay constant in the axion case, you have a shorter neutrino signal, which at some point becomes unacceptable to explain the late time neutrinos. So that's the usual story, I think, with the axion bound within the conventional simple model. And simple in the sense that it's assumed to be a neutron star and nothing else around it. So what are the caveats that you should keep in mind before I go into any other, maybe more less fashionable explosion mechanisms? So first of all, the simulations nowadays of the neutrino mechanism are very sophisticated, three-dimensional. They use GR, neutrino transport, magnetohydrodynamics. But they're still not at the point where you understand like, for example, what is the connection between progenitors and explosions, and how do you explain all kinds of observations. I think the community would agree with me. You can see this review, for example, by Boros and Vartanian from recently. So it's not a done theory, let's say, but it is very advanced. There is one question that arises when we looked at this, and it's not the main point of our study, but it's still, I think, interesting, because I don't know the answer. So again, the axion bound and the subsequent Raffel criterion usually assumes a bare neutron star. And the question is simply, is that a good enough calculation? Because I told you the neutrino-driven explosion requires instabilities, etc., which means you need 2D and 3D simulations. And when people are doing these kind of simulations, they are reporting that they see some residual accretion. I mean, some of the star explodes, but maybe some of it falls back. So even within the normal, the conventional model, there is the question of whether the late-time neutrinos came from residual accretion. I think this was studied in the 90s with thinking about one-dimensional explosions, but I don't know of a study with 2D or 3D simulations in mind. And the last thing that I know that there are some statements about indications of neutron star. I'm happy to go into it offline. As far as I'm concerned, I don't know of really robust detection of a neutron star. If you are really convinced that there is a neutron star, please, I'd be happy if you try to convince me. So that's that. Any questions so far?
You said that you would like to, you will be happy to discuss it offline. I mean, you know that there is a hint or a claim that the neutron star has been hinted or observed by ALMA. There is an analysis and so on. But maybe, yeah, maybe we discuss it offline.
Yeah, there are at least 2 papers about this that I know of. Yeah, I'm happy to discuss it later. And
yeah, because there is the ALMA paper, and then there is a of astrophysicists and Sigan and collaborators, I think it is. They put the reference in my paper. Janka is involved.
Yeah, I'm familiar. I'm happy to.
Okay.
But it's true. There are at least 2 papers that claim some indications of a neutron star there, which could be true. So I think just at this point there should be. It warrants a little care when you adopt the supernova bound on new physics. Now I would like to go to an alternative model on which much less people work on, much less consensus, and yet it's interesting to consider for reasons you'll see. So this model does not posit that neutrinos explode the star, but the thermonuclear material in the envelope of the star, like helium or oxygen, they are in charge of exploding the star. So this was suggested back in the 50s and subsequently studied in a few works, which thought this doesn't work. And it was revived by Kushner and Katz and subsequent works, also with Bloom, which showed that thermonuclear explosion can work in some rotating progenitors. And there is an asterisk here because initially the progenitors that they looked at were tuned to some extent. So there's still the open question of whether they occur in nature. So it's kind of a model in a much more preliminary stage, but still it's interesting to consider its implications. So again, I'm going to use the pictorial picture. I'm going to say initially the model basically agrees with the first model I told you about. But then it assumes that the neutrinos fail to explode the star, and accretion just continues. You can compute it easily and show that after a couple of seconds, you expect a black hole to form, which begs.
Is there any question online?
Yeah, JMC.
Well, if not, you can proceed.
Okay. So, and I'm gearing this discussion towards 87A, I should say, and not a general discussion of all generalities of these of this model. So, after a couple of seconds of accretion, the black hole would form. Then it begs the question: where are the neutrinos and where is the explosion? So I told you you need rotation for this kind of model to work. So after a few seconds, an accretion disk forms, and that is in charge actually to both the neutrinos and the explosion to some extent. So here I'm showing you a snapshot of a simulation from Bloom and Kushner, which simulated such this model having an accretion disk that explains the neutrinos in 87A in mind. So these are circular coordinates where you see that in the very close to the center there is a red blob from which neutrinos are emitted, and far away you see that there is an outgoing shock wave which comes from when you create the accretion disk. There is a rotational induced shock wave that launches. In any case, the neutrino luminosity, if the material is sufficiently hot, you can easily estimate the neutrino luminosity, and for plausible values of accretion and disk radius, you find that a luminosity scale which roughly agrees with what you see in 87A. And here it's also took a while, sorry. Here it's a graph of the luminosity and the energy scale of the neutrinos emitted from the disk in the Bloom and Kushner simulations, and it roughly agrees with what you want for 87A. So in that sense, there is a proof of concept that an accretion disk could explain the late time neutrinos that we observed in 87A. Again, I want to put this in the picture of the data. So it would look something like this, what I told you. The initial part, it's like the first phase of the explosion, is accretion plus proton-neutron star cooling luminosity. And then there is a black hole formation, which roughly explains the gap that I first showed you in the data-driven analysis. And in the end, you have a phase of renewed accretion luminosity from the disk, which I showed you in the last slide. So from a statistical point of view, I think that this is a slightly better fit to the data compared to the first model, but not by a lot. And now I should mention that how does the explosion take place? By the way, how am I doing on time?
Please, go.
I'm okay?
Yeah.
Okay. So how does the explosion proceed? So it's quite different than the first model I showed you. So here I told you that when you form an accretion disk, an accretion shock launches, and it meets this helium-oxygen layer, which is not something that is generic in simulations, simulations of stellar evolution. It is something that maybe some calculations have seen, but it's still a work in progress to see if this helium-oxygen layer that Kushner used in his simulations, whether it's actually occurring in realistic stars. But in any case, when you do this, apparently you find an explosion. And it brings me to the last point of what happens to the accretion disk, which is your new method of emitting the neutrinos that you've seen in 87A. So how it is affected by axions or something else, some other new physics, of course. So there are two things which we need to check. The first one is whether neutrinos are emitted more efficiently than axions, in the sense that their emissivity, which is energy emitted per mass per time, whether the emission of neutrinos is more efficient than the emission of axions. So we took axion nucleon coupling from probably one of the papers of Raffeld, actually. And you see already that the emissivity of neutrinos is much more larger than the emissivity of axions for bare values which fit the accretion disks. Now, but this is not yet enough, because even if you did it for a protoneutron star, you would still see that the naive emission of neutrinos is much larger than axions. What you need to check is that neutrinos actually free stream and not diffuse. So here I'm showing like a back of the envelope calculation of what is the mean free path of neutrinos inside the neutron star, and you see that in a neutron star of size of a few tens of kilometers, the mean free path is less than a kilometer. So inside a neutron star, a neutrino diffuses, whereas axions, at least in the free streaming regime, they free stream, which is not the case for an accretion disk. In an accretion disk, you take the phase values and you find a mean free path of like 10 to the 5 kilometers, which is much larger than the size of the disk, which is maybe 100 kilometers or so. So axions turn out to be not as effective in cooling an accretion disk compared to the neutron star counterpart, in the sense that both emit the same luminosity of neutrinos. So that's the main point, at least novel point, I guess, that we made in this paper. So, any questions? Yeah.
So a couple of questions. What about because like, it seems that I understand there is an early phase, right? With the initial burst.
There is a what?
An initial burst of neutrinos, right? It is the first neutrinos you detect before the gap, right? That you are talking about.
In the first 2 seconds.
Yeah.
Yeah.
Why that is not affected? Like, I would imagine that if you, especially if you put a large enough coupling of the axion, you would have the large.
So we did some simulations that, well, that did not arrive all the way to 2 seconds, but they gave some indication that you have enough luminosity from accretion and not from the very dense part of the neutron star.
How things change, for example, because you're always doing everything in the free stream.
Mm-hmm.
Of
Mm-hmm.
I mean, which actually the change.
I mean, you're saying what if I
Go into
FA that is
10 to the whatever, like in GA gamma.
Mm-hmm.
With the neutrino one, that is when you stop because you say that you affect the relative transport, right?
So I suppose, well, we didn't go full to this point. I suppose, at least from my point of view, 2 reasons. One, maybe it's less interesting from theory point of view. Fear. Let's ignore him. The second, to me, it's like you can probably put bounds on new physics, assuming this model, but it becomes less interesting. I mean, you could go to a region. What was
I don't know if he refers to me on Nitsan. We are both in Israel, so we are both in danger.
Filippo, can I stay here?
Please, please, please.
Can we open the chat? I don't know.
No, but maybe if you want to, maybe it's easiest if you finish your reply, complete your reply, and then
I have a couple more slides.
we let clear. No, sure. But I don't know if you completed your reply to Andrea.
Roughly speaking, I mean, what I started saying is that you could, in principle, take this model for granted and then derive other new physics bounds, maybe. But it seemed to me like we don't understand enough about supernova. I mean, this is to me the take-home message.
I mean, I don't know, because like when you, it's true that we don't understand much, but at the level of back on the envelope, right? I mean, if the mean free path of the axiom becomes comparable to the one of neutrinos, for sure you're affecting stuff, right? Because typically you move energy through neutrinos, right? And if axion become the same mean free path, you will, right? I mean, like,
let's say like this. Okay, we mostly focused on the regime that
free streaming. Okay, that's okay.
Yeah.
Yeah, Philip, if you wanted to add something, or anyone from the chat,
you can unmute yourself. Should work, I think. No.
Hey, yeah, but no, I don't need to jump in, but I'm happy to discuss at the end.
Okay. Then please, Nitsan, move on.
Yeah. Since I don't know anything about the topic, I wanted to ask, why is the second model popular among professional astrophysicists?
I don't want to answer for them. I mean, I don't know if it's how much of it is scientific and how much of it is less.
What this
I suppose there is criticism, for example, on the kind of progenitors that are used. That is, for example, an open question of whether the progenitors that were used to explode such stuff like what I've shown you, they don't come out in stellar evolution models, at least the standard ones. And there are, I suppose, maybe other models as well. It's a community that this is one thing that was close to us, I suppose.
Related to this, you were showing earlier a slide where you were saying about the work that started in the 50s, looking at these progenitors and then black hole. Can you remind me, they were not taking into account rotating progenitors? Is that what it was? And now, I mean, what's the main new ingredient in this starting in 2015?
Their assumptions. But again, for example, to get explosions, Kushner had to kind of tune progenitors to get explosions. So it's still in an early stage.
But also, sorry, what do you mean by that? Exactly what do you mean he had to tune the progenitor? He had to tune?
It's taken, standard stellar evolution model of a progenitor and he ran the simulation. I guess it didn't explode, but then he said, what if there is a slice here which is a little more mixed, for example? And there are some motivations for it from some more new calculations, but it's still, I think, unclear if such progenitors exist in nature. Okay.
Yeah, thank you.
Could you develop a little bit on what it would take to it's basically a binary question, right? I mean, is there a black hole left or is there a neutron star left? So what are the kind of perhaps even indirect signatures, observational signatures to settle that question? I mean, is it morphology, chemical signature, whatever? So I'm curious about that.
What is the remnant in 87A?
Yeah,
I don't know.
to settle, yeah.
I don't know what, I mean, for example, had they measured the pulsar by now, it could be a very good evidence for a neutron star. But I don't know how would you settle it soon. It's not something I worked on directly.
We are in the discussion session or
There were, but there was often a slide after the summary.
finished done.
And do not underestimate summaries, right? So to summarize, accretion is a generally natural neutrino source that could have supplied the neutrinos in 87A. So I would call it preliminary work, I guess, on collapse-induced thermonuclear explosion, indicates that an accretion disk could have emitted neutrinos, as well as triggering the detonation of the material in the envelope there, thus explaining 87A. So in that kind of scenario, the axion bound is lifted. And again, to mention the smaller point, which is an open question for me, which might have been answered, I don't know, that recent 2D and 3D neutrino-driven explosion simulations have raised hand. I just finished the sentence. So recent simulations report some residual accretion after the explosion takes place. So there's an open question for me that whether this could supply the late time neutrinos in 87A.
Please, Samuel, if you from on Zoom.
Oh yeah, sorry. I was just kind of getting in line for after he finished reading the entire slide. I didn't want to interrupt that. Yeah, please go ahead.
Okay. One last thing. So I was asked a few times, what is the outlook? So I guess for me, new data. So I don't know much about the optical part, but it would be interesting to see new data from other supernova. So there's the obvious one, which I also worked on, the next galactic supernova, which might take place sometime soon. Then we'd be much wiser about supernovae, and that would be very nice. Possibly another thing is this megaton MEV scale neutrino observatory that could give you in principle extragalactic supernova signal on a yearly basis, which was talked about long ago. I don't know of any progress in this direction, although I'm sure particle physicists would be happy to have such a detector. So that's what I can name in terms of what would excite me to revisit the supernova. That's it.
Thank you very much. Now we take maybe first Samuel question that was waiting, then we move back here.
Yeah, I'm curious what.
Yeah, hey. So yeah, I think half of people probably know I'm a true believer in the bounds, let's say. So that there was a question earlier about, why are resources devoted to one kind of theory for this outcome of this collapse and not, this particular one that was discussed here in a nice way. And I mean, the original paper was titled the Burroughs and Latimer paper in 1987 or 86 was, the birth of neutron stars. The mystery is, why are there neutron stars? We see them, all around, and they're really mysterious, interesting objects. And, having an explanation of why they come about at a kind of heuristic level is very interesting. Nuclear material stiffens and throws off the overburden. And if we didn't know of the existence of neutron stars and all we had were these kinds of simulations, I think it would be very, this would be compelling to say, that actually doesn't work, that stiffening does not result in a stable compact object at the end. But neutron stars are common. Pulsars are not, particularly rare objects. And so the question is, what happens during core collapse or after core collapse? And there could be, a kind of large number of possibilities, a zoo of end states for that process. But I think the kind of conservative, reasonable possibility that most of them result in neutron stars, and that supernova 1987A was a typical one because it has that neutrino cooling signature that has been predicted. That seems compelling. And that's not to say that there can't be other possibilities, but that I think the interesting question is, what's the balance of those things, and how do we know, and how do we assess what happens at the end of these stars' lives? But that's what I was going to say. So anyway, it was a nice talk, and happy to hear other things. I just didn't want to go on a long diatribe in the middle of it.
Okay, I'm not sure I understood if there was a question. I can say that there are neutron stars. Some of them could have originated in a neutrino mechanism explosion. Some of them, I think, can also originate in a collapse-induced thermonuclear explosion. I think if the progenitor is sufficiently light, this is what Kushner reported. It's true that there is, as I said, it like first order, the neutrino signal has the time scale consistent with a neutron star formation and cooling, but it doesn't exclude a different possibility. But Kfir said that he can add more, I guess.
Yes, if Kfir, you have anything to add on this specific point, otherwise move to other questions.
Yeah.
Please.
It's a good question by Sam that I already answered him in the past. But now let me answer to everybody. So the good question that I see is, how come there are neutron stars? Because Nitsan described the process that could potentially explode stars and not leave a neutron star. So how come there are neutron stars? And the simple answer, which I think we already explained in the past, is that simulations of this collapse-driven supernova explosion leave neutron stars in many cases. They seem to leave black holes in other cases that are in fact more rare, as 87A was. 87A was not a particularly typical supernova. it in fact was a high energy supernova. So the released energy is in the ballpark, kinetic energy of ejecta in the ballpark of 10 to the 52 ergs. And the simulations are finding that for high energy explosions, you tend to leave black hole remnants. And for low energy explosions, around 10 to the 51 erg in the ejecta, then more often than not, the bound remnant is in fact a neutron star. So this process can definitely leave neutron stars, should leave neutron stars. How many, I don't know. If it's reasonable to think that all supernovas leave neutron stars based on counting, I don't know. I don't think Sam knows either. I don't think anybody knows, but it's a good question to check. So yes, this process can leave neutron stars. I don't think there is any obvious problem in this respect.
Okay, thanks. It was Andrea.
Okay, thanks again for the talk, Nitsan. So it's a question for you and Fear, whoever wants to reply. Given that we were like talking about these new observations, also like even if you said that you don't know much about the optical, let's say, or like the spectrum counterpart, right? But it's an important question because there were observations from Chandra also, like, and Alma, right?
Mm-hmm.
In which they were claiming that they were seeing some X-ray signal. It was consistent with the non-thermal emission from a remnant of a neutron star. In your scenario of a leftover black hole, do you have an explanation for the spectrum that they see?
I don't know of an attempt. Okay, given that observations have actually measured something, which is not an obvious question. Like it's not obvious that they measured the signal. If they did, you'd have to look how to check whether. I mean, I didn't go into the details of seeing, for example, if ALMA can be really explained by accretion.
Right, exactly. That was my question, basically. If, like, with some accretion model, you can explain the observation they have, because I assume that the temporal evolution of both like X-ray and then also radio stuff would be very different, right, in your scenario and the usual neutron star scenario, right?
Supposedly, but yeah, I didn't go. I didn't go as far as trying to explain the presumed signal with accretion, an accretion disk.
Okay.
Can I? No.
I can comment on this too.
Yes, exactly, please. Yeah.
Yeah, I think Nitsan worked a lot on the neutrino signals, but there are aspects of this that you're asking, and it's outside of what he worked on, and I think it's not his fault. Maybe I'll ask Andrea, did you read this? So two papers were mentioned by Andrea and Jorge. I asked both of you, did any of you read any of these?
Yeah, one led by Emanuele Greco, for example. And, you know, like as Nitsan said at the beginning, it's true that it's not conclusive, right? But but say that.
Okay, let's open one of them and see what they say. So actually, if you want, I think this is a very important discussion. And I'm very happy to just open them together. We can do it right now if you want. I even have some slides on one of them. We can open the other. If you actually read them, none of these papers is making a claim of a detection. None of these papers is claiming, in fact, that a neutron star is more compatible with the data than other explanations. So for ALMA, it is diffusive shock acceleration. That is the alternative hypothesis. ALMA doesn't even resolve the neutron star area. They're looking at the whole remnant. And the first paper is based on theoretical models of the neutrino-driven supernova explosion. So none of them actually, there is no right now observation in the data. If you look at the papers, that's what they say, that actually refers the neutron star. Let's look at them. So if you want, maybe you guys, it is a workshop. We can just do a discussion and open the papers and look together on the screen.
I mean,
yeah, why not? Please. How do we do this?
I have slides in one. Oh, you can just open.
Yeah. Yes, okay.
Yeah.
Let's move to other questions while we move to screen.
Sorry, Nitsan, while they do this. Yeah. What about another of the signals of gravity waves that are becoming popular? Gravity waves, no, supernova.
Yeah.
Gravitational wave emission, right? People are trying to look for those coming from supernova explosions. So with these mechanisms, can you kind of predict a gravity wave spectrum or something?
It's an interesting question. I don't know, actually. I didn't think about it. Whether, for example, an accretion disk could leave gravitational waves in a detectable size.
I don't know yet. You need to know the population and then see if they can be I mean, one of the supernova are a source of gravity waves that people look for. So maybe.
Right. Yeah, I haven't studied this.
And what about
I don't know from which phase in the explosion do people usually talk about gravitational waves.
I don't know. And what about this? For the supernova also, there is a diffuse background, right? That people have computed.
Diffuse neutrino background?
Yeah, I guess there will be something similar with this.
Which sense?
I don't know. Like, I'm trying to think about other signals that may distinguish these two scenarios. You have a kind of Bayesian view of how can I go from one to the other.
A diffuse supernova background, I don't know how it will. I suppose it depends on some unknowns, which would be difficult to. I don't know how I approach it from this point of view. I think a burst is more. Would tell us more.
Maybe someone else in the audience knows more, or on Zoom.
I mean, I think the gravitational waves would come when the quadrupole moment is biggest, so when it's most dense but most asymmetric. So it'd probably be at the collapse time, which is probably pretty similar. And for the diffuse background, it would probably be when the largest number in energy are given also at the kind of collapse moment in the first second. And so I'm assuming, it depends a lot on the threshold, actually, that statement I just made, but I would assume that it would be the same within a factor of, a couple. But those are just guesses.
We looked at the diffuse supernova neutrino, and it's interesting. But the difference is small. The difference is in the ballpark of a factor of 2 between the two models. So I think it's not going to be trivial to use this, but it could be useful when detected in principle.
And there are factors over the 1, for example, in the oscillations or the supernova rate which I wouldn't know. So that would be problematic, I guess.
Yeah, so maybe other questions from the audience or from Zoom. Otherwise, you can follow. I'm happy to follow with whoever is interested. Feel suggestion to look into this paper together.
You can share, Kfir, maybe you can share the paper and.
Yeah, please.
Okay. So tell me which one you want to look at. I have. Yes, that
We
happens.
saw Andrea's email, and then.
Yeah, that happens. You didn't say the previous ones, I hope. You know it? Okay.
Yeah, now we see your. We see some keynote.
Yeah. So I have a keynote with the first paper that I actually diluted this paper. I don't know if this is one of the 2 that you were thinking about.
I've read was the one like really the observation by like X-ray.
You want the ALMA? I think it makes
no
less.
this one? Yeah, exactly this one. Yeah.
Okay,
one,
sure. Yeah. But I think the previous one is more interesting, and it's also entertaining. So this one, just very quickly, and you guys can look at the details, or if you want, we can also just scroll really in the details together. So the possible physical, so first to understand, maybe just to look at what they see, just to understand. So this is the remnant Presumably the remnant, so this is the whole right SNR, and presumably the remnant in some smack around the center, or of course it could float away, right? Because there should be some kick velocity to the neutron star or whatever remnant it is. So it's somewhere around here. But the point is, when they do the analysis, there is a hot blob of gas that was identified before, but they're not looking at it. They're looking at the whole remnant and looking at the total model spectrum of the whole remnant. So that's the first thing to understand. We're not zooming in on a neutron star and seeing neutron star. We're looking at the whole mess and trying to understand what it does. And we can see together in the text where they explain that. The point is that they're saying the possible physical mechanism for the spectrum that they get, it's just the spectral information in a very wide range, is twofold: diffusive shock acceleration or emission from an absorbed pulsar wind nebula. So it is absorbed, that's important. You cannot see the actual claimed pulsar wind nebula, you have to process it through modeling some envelope.
I agree, yeah.
So where do you see that? So they're saying DSA cannot be firmly excluded. Let's scroll, you can tell me where you can see that.
That is precisely what they do when they do also the chi-square analysis. What they say that they find that they will need more data, of course, like we were also saying before, like Ray. But when they compare the models, even if you scroll below, when they go, for example, in the discussion and conclusion, they see that it seems that as compared to the diffuse shock, right, the absorbed PWN is favored in their analysis.
But by what? By what?
I mean, the thermal emission of data. You see, for example, at the spectrum and the chi-square, right?
Where should I look?
For example, page 4, at the end of page 3 and page 4, they discuss the fit and the chi-square, right?
Yes.
They say they find, like, a little bit more favor the PWN, and then in the discussion.
So where is it? Let's see.
So good description of page 4, and then all the discussion.
Good description.
Page 4.
So
a good description of the observed spectrum. We then repeated the simultaneous fit of the data from all years, obtaining blah blah. All the discussion there.
Sorry. Do you want to share it maybe? Because I'm not sure exactly where you're looking. I see here the chi-squares of two things.
Right. These two. So that is the first thing when they have a chi-square.
And as you know, so there is no difference. But as you know, statistical significance of this chi-squared, whether it agrees or not, I mean, it really matters what you put in there.
Well, sure, but it's still like it's favor respect to the others, and then they also comment on what they will look for, right, in the future to confirm one instead to the other.
Right, but the future is great, but we are talking about the present, right? You're setting a bound. So in the future, of course, you can find a black hole, you can find a neutron star.
No, but of course, like, my question is like with the axion, if you take, so they have an explanation and the fit is not that bad to their, with their simulation, right? I agree with you. This has to go through the simulation of supernova, right?
No, what has to go? I mean, I don't understand. First, there is the claim that it was said that there is in this paper a detection of a neutron star.
No, it's not.
Where?
An indication. It's an indication.
Where is the indication?
Well, it's consistent with their model, right?
It's consistent with diffusive shock acceleration. Right? What am I missing?
Yeah, 1 sec. There was a comment without mic. Please.
Hi, Kafir. I'm Jorge.
Hey, Jorge.
Yeah, I read this paper some time ago.
Yeah.
Claim that they make any statement whatsoever. I agree with you.
Okay. So wait.
However,
so we can put this behind us.
Yeah, well, I don't know. I mean, you are far more expert than me on this. So, but I think the other paper is it's a statement, right? And the title.
You mean this one?
Yeah, that one.
Oh, this one is beautiful. This one I'd love to talk, but let's put this one behind us. So you want to? So let's do discussion.
I would love. I mean, I don't know if everyone is interested. I would love you to guide me through this paper and see.
This one I can guide you very quickly in 3 slides, and it will be very clear.
Please.
This one, but let's finish with this one. So there is no significant statistical preference of the pulsar wind nebula over DSA. Theoretically, apart from the fact, if you're biased that there must be a neutron star there, sure, you're convinced. And I would say that if you want a proof of concept that there could be a pulsar in there, that's fine, you have it. I think it's perfectly fine. I don't think, let's say it this way, it's a non-trivial statement to make, but I don't think the observations rule out a neutron star in the remnant. And that's good, they could have ruled it out. But if you want a proof that there is a PWN in there or a neutron star in there, you don't have it in this paper.
No, the opposite if you want. Like my comment was, I mean, question to Nitsan was like, in your model that I'm not familiar with, right? In which you leave a black hole, right?
Yes.
Does your model like correspond, for example, even in this paper discussed by Emanuele Greco, would you like just the diffuse shock acceleration scenario, or in your model you would predict something else? This is what
excellent. That's excellent. So first, there is a shock. We see a shock, and there should be a shock. There was a blast wave, and there is a shock. So a shock should be there, and diffusive shock acceleration at some efficiency should be there. Is that what we see? I have no idea. So DSA in both model, at some level, has to be there. Okay. So let's start with that. But or any model, there is a shock, there should be some, and it's magnetized, we know it. There is some diffusive shock acceleration. Again, I don't know how much energy it releases in X-ray, etc. Now, what you're asking, if there is a black hole in there, there could be accretion. And the accretion onto black hole, even at late time, could in principle release energy, even just Bondi accretion on the black hole.
Right.
This was simply not modeled. Why? Because there is strong bias for a neutron star. So
right, exactly.
this model was not tested. I think it is.
I agree. Yeah, but it's interesting, no? Because like imagine
very interesting. Yeah, and maybe you could rule it out. I doubt it, but maybe you could rule it out. Okay, but by studying the accretion from just embedding a black hole in.
Yeah, even Eddington accretion, whatever accretion, then you have some prediction. Let's say.
Absolutely, absolutely. It's very interesting. We started to look at this and other systems from X-ray binaries and other systems to try to ask ourselves, can it be that some of these systems could be accreting black holes? I don't know the answer. We need to agree at this point, or not agree, right? Or discuss. Are you with me? This paper that we're looking at right now is not making a claim that there is a neutron star in the remnant.
On this I thought, yeah, and this I thought
it is finding, it is a proof of concept. It is consistent. It seems to be compatible with the data. It is a very complicated analysis. It looks at the spectrum of the whole SNR.
Totally
not at all on the region of the remnant. It models the spectrum in a very complicated analysis, 1,221 degrees of freedom.
Yeah.
And the answer is completely compatible with just diffusive shock acceleration with a reasonable index.
Totally agree.
So
no,
can we put this
totally
paper
agree.
behind? So there were two papers that were mentioned. Let's put this one behind. So now
on this, I totally agree on this, but I still think that the question was, as you say, it's still there. Like, given this sophisticated analysis, would an accretion black hole that you predict to be there, be consistent with this?
I don't know the answer, and it's a good question, and it really deserves to be modeled. Okay, so don't get me wrong. I'm not saying there is a black hole in there. I'm just saying it was never excluded, and in fact, in this case, it's not modeled to the end. We don't know. So I just don't know. But there is a big difference between saying I don't know and saying I know there is a neutron star in there. Here there is a bound. Do not look for axions in that range. Okay. So let's.
Other paper?
Okay, this paper is really pretty. I love it. So here goes. Let's start with the very beginning in the abstract. Let me see. So first there is a hot blob, or there is thought to be a hot blob of dust in the remnant, as they say, and they say it even more carefully in the main text. Can you see my cursor?
Yes.
Do you see? Okay. So they say that the infrared excess could be the decay of titanium, whatever it is, accretion luminosity from a neutron star or a black hole, which again was not modeled really, magnetospheric emission or wind originating from a spin pulsar, or thermal emission from an embedded cooling neutron star. Okay, there are several possibilities. Some of them have a neutron stars and some don't. And in the text, they are more careful. We can go through it. Why do they really say that this is a neutron star? I dug in the paper. I really welcome you to dig afterwards and tell me if I missed something, but this is the only statement I found. Again, we can go through the paper and see if I missed something. They say the following: when do they really converge? We assume that the compact remnant is a neutron star, okay? They do the following. They're saying explosion models of this group for state-of-the-art progenitors 487A indicate the baryonic mass is something. These values are below the threshold to make a black hole. Therefore, because the simulations of progenitors that are supposed to lead to this, yes, predict baryonic mass below the threshold for black hole, therefore they will assume that this is unlikely that the object is a black hole. So they're going to assume that the object is a neutron star. But it's much more pretty if you just go a little bit more in the details. Okay, so explosion model state of the art tell us that this thing cannot be a black hole. So what are these models? You open the papers. Here is the paper. This is the paper from which the conclusion is driven. Three-dimensional mixing, explosions 487A. Okay, so you think to yourself when you read these titles that this star exploded in a supernova. But if you read in the details, you find the following, section 2.2. There was no explosion in any of these simulations. What happens is that the shock did not explode. It was stalled. They revived it. How did they revive it? They triggered it by hand by imposing a suitable value of the neutrino luminosity. Okay, so guys, understand, these guys, the simulations do not explode. They take the neutron star that they have in the simulations and by hand they trigger up the neutrino luminosity until it explodes. What is the explosion energy of the model? Explosion energy is what you put in. The explosion energy is determined by the imposed luminosity that we prescribe as well. The explosion luminosity is a free parameter. It is not coming from any simulation. It is put in by hand. Okay, that's the paper. So that's pretty amazing. What just happened here? This paper concluded there is a neutron star in the remnant based on the assumed mass of the remnant that they get from simulations. The simulations that they use for that assume the neutron star. Do you see where we're standing? That's what's happening here. So that's it. There is nothing more. If you want, I have the paper open. We can go into detail and look and find if there is any other place in the paper that converges them to a neutron star. I have it open, and if you want, we can do it. But you can also read yourself and you will realize it. I think it's a bit shocking, and I think you need to read these papers in the details. They're doing an amazing simulation job, but there is still some distance to make before we know what's going on in these explosions.
Yeah, I confess that this second paper I didn't read. I basically skimmed through it, and it seemed like they were making a data statement. But this brings me more or less to the general question, right? I mean, what's happening? I mean, I go and I watch Thomas Chanka giving the Sun Colloquium, and it seems from what he's saying, I'm getting impressed. Everything works. All, you know, they have now, they reach, according to them, a maturity in their simulations. They are doing 3D. They have these homogeneities that make actually the explosions to work. Not that you're saying that you need to inject some.
Well, I'm not saying that you need to inject anything. They are saying in the paper you were citing, they are saying that that is what they did. Now, what they say in colloquia or what they do in work, I think there is fantastic progress in what they're doing, and maybe they will solve the problem. But the problem is not solved now. So if you're quoting a bound on axions now, you're quoting it based on nothing.
Okay.
I think it's as simple, and we can debate. I think maybe they will make it. You know, it will be a spectacular success when they make it.
But I guess you guys talk with each other, no? I guess that you sit down and
sometimes
exchange emails. You say, hey, how are you? What do you think about this? I mean, because I mean, it's like two completely different interpretation of what's going on, right?
Yes.
From an outsider that is interested on the topic, right? It seems very confusing when I hear you both talking about the same things.
Right, but I think, this is really an informal workshop, and I don't think they are fairly represented here also, which is very, I think, important for the discussion. So let me just say that, I mean, I would say if you place a bound, make sure, you know, that you see what it's standing on. So in those papers, I don't know, maybe tomorrow they solve the problem. It will be spectacular, as I said. The papers that are claiming detection of neutron star have not done it yet. And we can dive in the details of numerical resolution of the 3D simulations and the initial conditions, if they're really coming from numerical simulations of stellar evolution or not. And the stellar evolution, can they even deal with stellar interior rotation or not at this point? So there are many, many astro details. It's a lot of work. Maybe it will be solved at some point. It's not solved now. So that's all I can tell you. And I think that the idea of collapse-induced thermonuclear explosion, it's old in a way, like Sam mentioned, but it was mentioned, you know, it was proposed in the 60s and then in the 80s with very low resolution, very simple, essentially 1 or 1.5D simulations. And there it failed. At the same time, by the same simulations, the neutrino mechanism failed. But the community picked up on the numerical or the neutrino mechanism. And now there are huge, you know, machinery towards trying to make it work. The collapse-induced thermonuclear explosion was abandoned. And it was picked up only very recently, in the last few years, with serious machines, you know, with the $2 million computers from some astro groups, and they are working on it. I think it's a new idea compared to decades of work on the other mechanism. It's still immature. And I don't know, but I mean, talk to me in 10 years. We'll see which one of these things wins. When maybe one of them is dead and the other is alive, maybe not, I don't know. But right now, I think
I mean, the reason for that original bifurcation is that the energy density vectors pointed in different directions. The initial simulations for SITE, all the energy pointed inward, and for delayed neutrino mechanism, it all pointed outward. And so that's the origin of it. I agree that it's worth, you know, revisiting in detail, but that was that's the
what do you mean?
Basis of that.
Sam, in
and you can solve that problem with a lot of rotation, as you have found. I mean, it's not impossible, but that's the kind of the origin of all of these points that I think are worth keeping in mind, is that there's kind of heuristic reasons and just the suggestion of typicality all kind of point to, you know, let's take a minimal assumption that just kind of seems to work versus something that, you know, if you set up just the right conditions, and then you see something in the same ballpark.
Yeah, I think some we diverge on this. I think, and there is a lot of subjective
I know we do.
There is a lot of subjective statements. I don't know if people are interested. We can talk about rotation and compare it to simulations. I have no problem. But again, we will see. I don't know. It's okay to not agree.
That's true. I actually had a question also for you, Kafir, about the statement you made earlier about the weak explosion energy versus strong explosion energy. I was just looking through your papers and I didn't see that, and so I was wondering, did that change since 2016? Because
no.
There you suggest that it was 10 to the 51 ergs was the strong.
Right, sorry, yeah, 1.5 10 to 51. I agree. Kinetic energy in the explosion. I agree with you.
That's the borderline between strong and weak explosion. And
roughly.
What observation do you trust that tells you that it's a strong versus a weak explosion?
So the explosion kinetic energy can in principle be measured from the ejecta. Basically, if you can estimate the mass of the ejecta and you see the speeds, you can estimate the kinetic energy. And what you can do, you can look around and find, do I see supernova remnants that measuring the kinetic energy of the ejecta suggests that there are strong explosions, and I can see neutron star in them. And
I'm just wondering, do you think there is an observational indication at this time that it's strong or weak?
What is strong or weak?
The ejecta around Supernova 1987A.
87A fell above the threshold from the simulations, and we discuss this in the paper. So this is from the simulations of Kushner.
So what's that threshold? So the threshold you suggested earlier was 10 to the 51 versus 52.
Let me open it.
Okay.
Yeah.
So
So we can discuss.
Yeah,
it.
sorry to distract everybody.
No, but
It
it's
is
fine. I mean, the
it
purpose
is in our
was,
papers, but we can discuss anytime you want.
yeah, the purpose was to discuss. And I mean, unless there is anything urgent from anyone here or in the chat, I would like to thank then Nitsan again, and also Kfir, Samuel, and the people that intervened, Andrea, for the lively discussion, and see you tomorrow 4 p.m.